So, well, what do we mean by solubility, first of all? Solubility. It's how much of a solid will actually go into solution. And what's the expression for that term? How do we express solubility? Usually, we express it in molarity. Right? How many moles of the solid per liter of solution? Now, if you look it up in a reference manual like CRC handbook, it'll usually give it to you in grams per 100 mils of water. And if it doesn't say what the temperature is, it usually means 25 degrees. This is for practical application. How much can you expect to put in 100 milliliters of water? This is what we're going to use for expressions of solubility so that we can do calculations. Okay, that's what we mean by solubility. So, and the solubility of any solid can be expressed in terms of the equilibrium expression has a subscript of SP. SP means solubility product. And it means solubility product because, well, let's use our example there. Right. Oops. Me. There we go. Now, this is, oops. Same ratio, but wrong element. Bismuth sulfide. This is a solid. It's in equilibrium with this ion in aqueous solution. And we're going to restrict our discussion to aqueous solutions. 2 of those and 3 sulfides. What we're implying here is that if this is in equilibrium, that means there must be some solid in the container. You should have some solid down here. And then you have your aqueous components up here. And like all equilibria, you got a dissolution and a condensation, solidification going on at the same time, equal rates. That's what that means. So we're actually, when we talk about solubility, we're actually discussing a saturated solution at any given temperature. Okay, so when we write the solubility product, remember we don't include solids. So this expression in these terms is going to be simply the bismuth squared and the sulfide cubed. That's why we call it a solubility product, because that's all you have. It's just a product. You don't have anything in the denominator. Now here's a place that may give you some trouble. It may not. When we say KSP, of course, that's constant for any temperature. But the question is, does it mean if you compare solubility products of different compounds, does that mean that the higher solubility product means that that solid is more soluble? And the answer is no, not necessarily. Because we have these terms that are involved with this expression versus the solubility of that would be in terms of molarity. Right? How much of this goes into solution? So we're going to work some problems where we compare solubilities of different compounds. And one thing that you can do is, if the solubility product is constructed the same way for each of the compounds, say we had different compounds down here, and the cation was always 2 and the anion was always 3, then yes, you can compare the solubility products for those. And the higher one's going to be more soluble. But if they differ in these terms, then you have to actually work out the solubility term before you can compare them. All right. Yeah, I just said that. There it is in green and red. Okay. So let's actually calculate the solubility of a sample. If we consider silver chloride, and in the past, right, in the first semester, we had this chart, and it essentially said this combination of cations and anions would go over. If the cell was grayed out, it was insoluble, and if it was clear, it was soluble. And there are rules that go along with that. And now we're going to refine that a little bit, because when we speak of soluble and insoluble, it's actually a continuum. Right? Extremely soluble over here, like sodium chloride, and what we had considered insoluble, silver chloride, on this end. But there's a grade. There's a grade in here. Some are more soluble, some are more insoluble than others. And now we're going to quantify that. So if we say that the KSP for silver chloride is 1.6 times 10 to the minus 10, well, that's extremely insoluble, but there's still a measurable amount of silver chloride that goes into solution. And we evidenced that when we did the Le Chatelier's experiment. Okay, so we're working from this solid producing these ions in solution. Okay, and this is going to be an expression of just silver ions and chloride ions, because their coefficients are 1 and 1. Okay, so if we set up our ice table like this, okay, let's put it out here. Of course, this term is not going to enter in to this calculation, but it's helpful to know if we know that we're going to lose some of this. In other words, we're going to lose some of that, then how is it going to show up over here? It's going to show up over here as plus X and plus X. But the equilibrium we don't deal with here, because that term's not in the expression. But it's useful to determine what to call these variables, right? If these are 0 and 0, then the change is going to add some of this into solution, and that's simply just X and X. So this is going to be X, this is going to be X. So we actually have X squared equals 1.6 times 10 to the minus 10, and we just take the square root of that. And that should give us the solubility of silver chloride in aqueous solution. 0.6 square root. So we have 1.26 times 10 to the minus 5 molar. That's the solubility of silver chloride under standard conditions. This is probably at 25 degrees. Okay, and that's what we should be doing here. Yeah. Well, that's right. I added an extra significant figure. It should be 1.3. Okay. What if we do the same thing for silver phosphate? Let's see, this is for silver chloride. So let's just keep that for comparison. And this is where, if you have a word problem that says, what's the solubility of silver phosphate? You got to know how to write the compound. I hammer that point in first semester with my students, say, you got to learn how to write these compounds. I said, it's going to come back to bite you if you don't. And this is an example of that. So here we have silver and phosphate, which is 3 minus. So this one has to be 3 there. That's a solid. So this gives us 3 silvers and 1 phosphate. So these ice tables for solubility follow a pattern. And if you need to, go ahead and write it out. But pretty soon, if you work enough of them, you'll develop an intuition about how to write this expression here based upon that. And you won't have to actually set up an ice table, right? If we lose some of this, we're going to show up as 3 of them over here, aren't we? Because we've got 3 there. And 1 of these. So this is 3x and x. And 1.8 times 10 to the minus 18 equals, this is 3x inside the term, but it's cubed. And this is x inside the term. So this is going to be 3 times 3 times 3 is 27. And x cubed and x is x to the 4th. Okay? So x would be this divided by 27 and take the 4th root of it. I'll do it in steps. We just divide by 27 first. Oops. 0.8. Okay, divide by 27. And that gives us, we're going to take the 4th root of 6.667 times 10 to the minus 20. Now, some of I think algebraic calculators have a root function on it. And you just have to look for it. Mine doesn't. So what I have to do is say the 4th root of that number is the same thing as that number to the 1/4 power. So I would take that number and then I would say 0.25 and call that the power. And that should give me 1.61 times 10 to the minus 5 molar. Yep. So, silver phosphate is a little bit more soluble than silver chloride. Not much, but measurable. And you couldn't tell that because the K value is much, much smaller for silver phosphate than it is for silver chloride. I think that's one of the points of this slide is to show that they're not comparable if the stoichiometry is different. Okay, that's how we judge the solubility in water. Now, suppose we have a common ion already in solution. A common ion, that would be either silver ions or chloride ions or both in solution. Before you add the solid, how will that affect the solubility? Well, we can intuitively say that if there's already some in the solution, then it's going to reduce the solubility of the solid that you add. So in this case, where our example is silver chloride, how does that compare to silver chloride in acidic solution with nitric acid? Well, look for the common ion. Is there a common ion in the added acid? And no, there isn't. Right? Hydrogen ions, nitrate ions. We know that silver nitrate is completely soluble, so it's not going to affect the solubility. The solubility in that acidic solution should be exactly the same as water. Right? Because there are no common ions between the two. Now, if we were to use hydrochloric acid to acidify the solution, that would definitely have an impact on the solubility. But we're going to switch gears. We're going to use nitric acid again, but this time we're going to discuss silver phosphate solubility. And if we combine these two equations, because they're both in the same solution at exactly the same time, so they can interact with one another. So what's the impact? Well, nitrate, again, doesn't have an influence on the reaction. It's a spectator. But we know from experience that this acid produces H2PO4 minus, and H2PO4 minus can ionize another hydrogen and HPO4 2 minus, and then HPO4 2 minus can produce another hydrogen, and that's PO4 3 minus. This is where we're at in our silver phosphate. We know that these are all weak acids. This is the weakest. So this makes that one, this is the weakest acid of the bunch because of its K values. That makes this the strongest conjugate base. It's looking for hydrogens, and it's gonna snag them anywhere it can. So we're putting hydrogens into that solution, and it's going to suck up the hydrogens. Right? So what impact does that have on the solubility? Well, we look at the combination of these, the nitric acid, actually the hydrogen ions is what we're focusing on. And we find that silver phosphate becomes more soluble simply because this overall reaction, I'm going to leave out the phases here. 4 3 minus. These added hydrogens here snag those guys right there and produce that. So Le Chatelier says we're removing these phosphates from solution by this reaction, and it'll grade through these, but it's still picking up phosphates, and that drives the reaction to the right, which makes silver phosphate more soluble in nitric acid. And that's one way to increase the solubility of any compound, is to look for a way to remove ions, and they have to still be soluble. Remove ions from either this side or actually the first possibility for increasing solubility is to attack the anion. Get that anion out of solution and drive the reaction to the right. In a minute, we're going to look at when that's not possible, then you go for the cation, and that's where complex ions come in. Right? But the first one we're looking at is, can we remove that anion by some some coupled reaction. And in this case, we did. How does the KSP for silver phosphate in water compare to that of silver phosphate in acidic solution made by adding nitric acid? How does it compare? It's exactly the same. Just because we added some acid to the solution doesn't change the character of that reaction, and we characterize it with the KSP. The only way we can change the KSP in this case is temperature. So the KSP stays exactly the same. We can change the solubility, but we don't change the KSP. Okay, how about this one? Calculate the solubility of silver chloride if we have 100 milliliters of 4 times 10 to the minus third molar calcium chloride. We do have a common ion there. That's the chloride. So this is going to alter the solubility of silver chloride. In fact, it's going to make it less soluble, right? Because we're adding chloride ions on the product side, drives the reaction back toward the solid. So we've got, this is our reaction. Again. Okay. And we have an initial concentration. In this case, we have 4 times 10 to the minus third molar calcium chloride. What concentration, though, is the chloride concentration? It's twice that, because calcium chloride is completely soluble in water. So we're going to have 8 times 10 to the minus third molar chloride ions as our initial condition. And we're saying that this is before the reaction takes place. So the change then is still going to lose some of this, and it's going to show up over here, right? And at equilibrium, our expression is going to have an X here and an 8 10 to the minus 3 plus X over here. So we're going to take this expression and say 1.6 times 10 to the minus 10 equals X times 8 10 to the minus 3 plus X. Okay. X, we've chosen X to equal solubility. What's the solubility of that solid? We know, right, we've assessed this intuitively or qualitatively as a reduction in the solubility, because we've already got some of this common ion. It's going to, there's going to be a backward pressure, so to speak. So we know that X is going to be very small. In pure water, the X is going to be 10 to the minus 5 molar. It's going to be a lot less than that here. So that means that we can ignore that X. Right, so this is approximately 8.00 times 10 to the minus 3 X is equal to that value. And X then will be this number divided by that number. And 8 exponent minus divide. And I get 2.0 times 10 to the minus 8 molar. So the solubility went down about 3 orders of magnitude because of that common ion effect. Okay. Now we could go in and do the 5% rule, but trust me, we're going to make it. And the other point here is this is a type of word problem, and it says 100 milliliters of such and such molar calcium chloride. Does the 100 milliliters matter? No, not at all. That's blue smoke. It's like a car with burnt valves. Okay, let's see. We're still going to use that expression. So let me leave this up here. And we'll just remove that. What's the solubility of silver chloride in calcium nitrate? Calcium chloride is completely soluble. Silver nitrate is completely soluble. So there's no influence. There's no change in the solubility with calcium nitrate on the solubility of silver chloride. So it should be the same as water. Right? Not a common ion. So there it is. Same solubility as before. All right. Now here's what we're getting at next is I dropped my lid. What we're trying to introduce with this subject is ultimately, and one of the basic bench chemist technique for separating metals, a mixture of metals in solution, metal ions, was to adjust the concentration of various anions to selectively precipitate metal ions. Sometimes they come out in groups, and then you'd have to further process them. Well, the way to assess that is to compare the KSP to the Q. If you can calculate the Q for any given reaction here, and it would simply be that concentration and that concentration. If the Q is greater than the KSP, then you will get precipitation because this is too big, right, in that expression, and it's going to drive the reaction back this way. If the Q is calculated less than the KSP, then you will not get a precipitation under those conditions. So it's simply what is the concentration of the metal ion that you're interested in, and what's the concentration of the anion that is being used to precipitate. It wouldn't do us any good to calculate this if the anion were nitrate. That would be foolish. But we know that silver chloride does precipitate with the chloride ions if the conditions are right. So the Q has to exceed the KSP in order to get that precipitation to occur. All right, so we're going to start off with simple example. If we have a solution with barium and silver together in the same solution, and we want to separate them, silver chloride will precipitate. I think barium chloride is soluble. Is barium chloride soluble? Yeah, it should be. It's an alkaline earth. Barium chloride should be soluble. So what we want to do is just increase the concentration of chloride to the point where the Q, the calculated Q, exceeds the solubility product. So we could use sodium chloride to deliver our chloride ions, or we could use hydrochloric acid. Hydrochloric acid would be preferred because it won't contaminate the solution with another cation. Then you'll be stuck with sodium and barium together, and what do you do then? So we prefer to use hydrochloric acid to precipitate the chloride. And And then barium would still be left in solution. So if we knew that barium and barium and silver were the only two ions, cations in solution, then we could precipitate the silver chloride by increasing the concentration of chloride to exceed the solubility product. And then how would you get the barium out? Which evaporate the water. Okay, so in this example, we have a more complex mixture. We've got copper 2 plus, mercury 2 plus, nickel 2 plus, and manganese 2 plus. And we're going to try to selectively precipitate with the sulfide anion. The hydrogen ion is irrelevant, at least for the precipitation part. But the hydrogen ion does involve this overall reaction. Right? It would dissociate one hydrogen at a time, but for our discussion purposes, we're going to put the combined reaction because the precipitation occurs with the sulfide ions and those cations. So how would we control the sulfide concentration in this solution so that we could selectively precipitate? Well, if we acidify the solution, say, we could do that. Acidify the solution with hydrochloric acid. Then we'd be adding this, and it would decrease the concentration of that anion. So it would make it so low that some of those would not precipitate, but one or more of them would precipitate as long as we the sulfide concentration times the concentration of the various cations exceeded their solubility products. So we would try to take out the least soluble ones first. Right? And then if we added some base, then we could remove this, drive it to this, and increase that concentration, and that would allow us to take out the next group, exceeding their solubility products. So that's the plan. Okay. At low pH, because of added hydrogen ions, then the sulfide ions will be able to precipitate mercury 2 sulfide and copper 2 sulfide. Like this, because, the overall K for this is 10 to the minus 20. So all we have to do is decrease the sulfide concentration by adding hydrogen ions. And then we would add the hydroxyls, and that would shift the equilibrium to the right and give us more sulfides. So this is the flow chart for that plan. If you have those 4 cations in there, then you would decrease the pH to around 2. And that would precipitate the copper and the mercury and leave the manganese and the nickel in solution. Then you would add some base to exceed about pH 8. And that would precipitate the manganese and the nickel. Okay, so if we extend this procedure, then we get this sequence of events that can be used to separate that very complex mixture of cations. We would, of course, go for the chloride precipitation of silver chloride, mercury 1, mercury 1, and lead 2 plus. So with the chloride ions, we could remove silver, mercury 1, and lead 2 plus. Then we would add hydrogen sulfide because the solution's already acidic. And then we could get out group 2. These are acid insoluble sulfides. Copper 2 plus, bismuth, bismuth 3, cadmium 2, lead 2, mercury 2. We might have mercury 1 in there. We might have mercury 2 also. So we get those in 2 different groups. Then arsenic, antimony, and tin would come out with sulfides because they have very, very low solubility product in for sulfides. Then we would increase the pH with hydroxide ions. And let's see, if we add sodium hydroxide, that's going to mess things up for sodium later, right? So you're not going to be able to determine sodium. Even if sodium is in there, you're going to swamp it with the added sodium hydroxide and later with the sodium carbonate. So the sodium hydroxide then would take out the more soluble sulfides, aluminum, iron, chromium, zinc, nickel, cobalt, manganese, and iron 2 plus. Then since the solution's already basic, we could add sodium carbonate, and that would add the carbonate ion in there, which would take out barium, calcium, and magnesium carbonates. And then what you would have left over were all the alkali metals because they're all soluble, and you would have ammonium left over. Right, ammonium. The only way to get ammonium out there would be distillation. You'd have to distill ammonia out. And that's the way we run Keldols to do protein analysis of forages. We would digest the solution and then acidify the solution. So you'd have to reacidify this solution and steam distill your ammonia over into, I'm trying to remember what we caught it in. I can't remember. But then you would analyze the ammonia separately. But the rest of them, the alkali metals, right? In fact, all of these groups would have to undergo secondary separations. This is just the first step. Now, if you wanted to actually recover the metals, that's one issue, wet chemistry. If all you wanted to do was analyze for their concentrations, right, you wouldn't even have to do this. You can take that whole solution and run it through your inductively coupled argon plasma spectrometer, and you could get their concentrations in your solution just like that. Of course, it would cost you probably $500,000 for the equipment, and then a trained technician. Okay, and there are other ways to separate the metals, and industry has found ways to do that more cheaply. Right? Lots of times, what they do is they generate, they get the ore and they pulverize it, and then they put it in this kind of soapy solution, and they add some other compounds depending on the metal they want, and then they stir it up really good. It makes a froth, and then the froth comes off. And I think I can't remember if the froth skimmed off the top contains the metal or if what's left in the solution, but there are a lot cheaper ways to do it. Right? We're discussing this one simply because we're on the topic of solubility. Okay, so I mentioned earlier, if you want to increase the solubility of a very insoluble compound, you can attack the anion, make the anion, remove the anion by some secondary reaction like our phosphate. But if that doesn't work and you need to get at that solubility, then the other way is to form a complex ion with the metal. a stable complex ion of the metal will remove it from, go back to our typical example here. Silver. Yeah, this is a good one. Chloride. We can't increase the solubility by removing chloride. We can't acidify the solution and remove chloride. So if we have this situation, then we want to attack the silver and form some stable, even soluble, stable soluble compound. By adding ammonia. Actually, there are two of them. And we would form this complex ion. It has to be ammonia. Ammonium will not work. And it still has the plus charge. And this is soluble. But we're still removing this one from that equilibrium and driving the solubility to the right. So that's what you guys did with adding the ammonia solution to your silver, and it disappeared. Right? You were forming this complex ion and causing this equilibrium to shift to the right. Now, this expression right here carries with it also a K value, and it's a Kf, formation constant. So this one, since all the terms here are aqueous in solution, this would have all those terms present in the expression. And so we'd have the product here. Its concentration. Then the reactants here, ammonia, this would be squared. So that would be an expression for the Kf for that reaction. And this would be this solubility product and this Kf expression. Those are both happening at exactly the same time because they're in the same solution. Now, this is the overall. This is the overall reaction. Notice we have two ammonias here. You can look at the formation of complex ions if they have more than one, what we call ligands. Ligand is like a leg, right? It's got two legs. We have two ligands there. This actually happens like a acid dissociation, acid ionization, one at a time. So you get an equilibrium expression for one ammonia, right? It would produce silver and one ammonia, and that would give you an expression. And then you add another ammonia, that gives you a second expression. And this is the composite of those. Fortunately, most of them, most of these, even if you have, I've seen 5, 6, and 7 ligands on a metal, even if you have that many, most of them are usually very large K values for each one of the steps, right? So it goes through each step and ends up at the bottom. Most of it ends up at this point anyway. So actually looking at each one of those steps is not as important as it is for acid equilibrium. Okay, this ligand, since that's a metal and it's electron deficient, the ligands are always Lewis bases. They always have the ability to donate electrons. Here's an example where we have beryllium. Let's see. How would we name that one? Just out of curiosity. Let's see, we have tetrafluoroberyllium 2, I think is the way you name that. Name the ligand first and then the metal. Second, and you say what the charge is on the oxidation state on the metal. I think that's right. But you see that each step has a very large K value, 4 powers of 10, 4, 3, 2, and 1. And when you combine them all, you get an overall 10 to the 12. So what that's saying is you essentially move everything to the right, to that tetrafluoride. And that's where we focus our attention. If this is, if we're interested in that particular reaction, we look at the overall. Okay, so this is just a reminder slide for what do you do when you want to increase the solubility of an ionic solid. And if the anion of the solid is a good base, then the solubility is increased by acidifying the solution. So the anion in this case, the PO43 minus, is a very, very, very strong base in the Bronsted-Lowry definition. So all you have to do is add hydrogen ions and you can drive that reaction to the right. But if that's not the case, then you have to attack the cation. And our example has been silver chloride.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ICE table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So if we're losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1:1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a +X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus, raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the negative 10. So we put in here 1.8 times 10 to the negative 10. And this is equal to, this would be x times x. So this is equal to x squared. So we can get out the calculator and solve for x. So we have the square root of 1.8 times 10 to the negative 10. So we take the square root of that, and x is equal to 1.3 times 10 to the negative 5 if we round that. So x is equal to 1.3 times 10 to the negative 5 molar. So that's the concentration of, let's say, our silver +1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? Right? We get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver +1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver +1 cation. Right, so ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver +1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. Right, so we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion, which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound, silver chloride. And next, we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at 2 reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those 2 reactions together to get our net reaction for what's happening. All right? So we're going to add our 2 reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right, we have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those 2 reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add 2 reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those 2 reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative third. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ice table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia. So let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ions. So the concentration, the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x, our concentration of complex ion is X, and our concentration of chloride anion is also X. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here, so we leave silver chloride out because that's a solid, right? But we have ammonia, so this is all over the concentration of our reactant, so this is over the concentration of ammonia. And notice our coefficient is a 2, so we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is x, and our equilibrium concentration of chloride anion is x. So on the right side, we would have x to the first power times x to the, let me take that out, times x to the first power. Right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative third. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative third. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. Right? So we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar, right? So that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride, right? So it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
By a factor of 10,000. Right. Okay. All right. So if we, and this is, Salcon has already done this, so I'm going to kind of breeze through these. These are the different values. These first two, actually, the first one is solubility product for silver chloride in water. And then the second and third are the individual K's for the association with ammonia. Right. So the K for the overall would just be those two multiplied by each other. Okay. So there's our overall, and there's the equation that governs the solubility of silver chloride in ammonia solution. And we're going to come back to that for our the lab, not this lab, but the one after it. Actually, the last lab, where we're actually going to do a titration to determine the KF for the ammonia reaction. Yeah, that's what we're after in that lab. So the K value here for that overall reaction is 10 to the minus 3, which is better than 10 to the minus 10, but still it's kind of small. That's why in order to get to increase the solubility to some significant amount for silver chloride, we have to increase the concentration of ammonia to a pretty high level. Right, you see 3 was an example, 3 molar, 6 molar, 10 molar is not uncommon. Okay, so there's our equilibrium expression, as we've already seen. And if we change the concentration of ammonia to 10 molar, then we get a similar expression to the one that you saw in Salcon's video. We just put in different numbers. And then the solubility, instead of 0.14, was it? I think it was 0.14, was with 3 molar. If we increase the concentration of ammonia to 10 molar, then the solubility of silver chloride increases quite a bit, 4 times more soluble. Okay. So all I'm trying to show with this sidebar is that you still have a lot of ammonia left in that solution. So if you pull it up to your nose and take a big whiff, it'll wake you up. And I will point this out, although I've done it before, is that this technique, this complex ion, only works with ammonia, doesn't work with ammonium. And the main reason for that is that ammonium has no lone pairs available. It can't act as a Lewis base, whereas ammonia can. So I think in our Le Chatelier's lab, we reformed the silver chloride. We reprecipitated it by adding acid, hydrogen ions, and ammonia turns it into ammonium, and that destroys its ability to form the complex ion, and then we get reprecipitation. Okay. The end. Okay. That was a short